Welcome back to the AutoML lecture. My name is Andre Biedenkap, and in this module, we're going to talk about dynamic optimization approaches. And in this first part, we want to motivate why we actually need dynamic optimization at all. To do so, let's take a step back and reevaluate how we have treated the optimization problem of AutoML. Right? And we often treat AutoML as a black box problem that you have also seen quite extensively in the prior lectures. So early on, we have already seen these different black box views. For example, in this view, we take the time constraint and a data set as input to a black box, which outputs an AI model. We also often talk about data and configuration space as an input to a black box, which then produces an optimized configuration. And we have also seen approaches of how to use foundation models in the same manner, where we have, for example, a dataset documentation and the data such that the foundation model can generate some code output. While all of these views can get us quite far already, they do not take into account what is actually happening inside the box. And this is going to be very crucial in this whole module, as these dynamic approaches will try to take this into account. Now, before we can properly take this into account, we should also recall how learning is happening, right? I would argue that many learning approaches are actually iterative. So that means we start with initialization of some model, which we then fit to the data. Based on the observed performance or a computed loss, we will then adapt the model. So for example, adapt the weights of a neural network according to the loss. And then we will repeat these steps, fitting loss computation and adaptation until our learning budget is exhausted. Now, there's a very simple approach to learning lets us explore and traverse different solution spaces, right? At every iteration, at every step 2, we are evaluating or fitting a different model to the data, right? And we will observe different losses according to how trained our model already is. Now, this adaptation then that is happening based on the loss should also take this into account, right? So we should be able to adapt on the fly to these different models that we are actually trying to explore and exploit in a sense by learning. Now, dynamic optimization, counter to the static optimization approaches that we have seen so far, can actually deal with these types of non-stationary problems, right? It can actually adapt on the fly and not just at the beginning of the overall learning process. And I want to give you a very intuitive example with learning rates and deep learning because it's very commonly talked about. So for that, recall that your update rule for the weights is as follows. You take the old weights and you adapt them according to your gradient with the loss function such that you get the new weights. Here, alpha is our learning rate, and we will look into how alpha actually influences the update rule on a very simple parabola. Now, if we have a very small alpha on this parabola, right, starting from here, we can see that we take many steps until we actually reach close to the goal. Here in these 50 steps that I have set in this interactive example that you can also play around with yourself if you click on the link on the slides, we actually get close to the optimum, but not actually hit the true optimum. If we set the learning rate small enough, but not too small, right, we can start to get closer and closer to the optimum. And here we hit it very, very close already. The y value is near 0, and the x value, according to the GeoGebra example, is already set to 0. If we set our learning rate way too high, then we start to diverge, right? Instead of actually creeping closer and closer to the optimum, we are going further and further away and actually spiraling out of control here. So we will never hit the optimum. And that's just what happens if you use static optimization for this learning rule, or static hyperparameters for this learning rule, I should say. But obviously, the view of this parabola doesn't really reflect what the loss landscapes look like in the real life or in the real world. We might have some smooth optimization landscapes, but I would argue that we will deal more with solution landscapes that look like this, that have some ruggedness to it, multiple optima, some ridges, and so on. Right? And what happens if we take a static learning rate In this setting, for example, starting from here, we might get close to the true optimum of this function or the global optimum of this function, but because we're always applying the same learning rate, we will bounce out here. And you can play around with this interactive example again and see if you can actually find a static learning rate that would allow you to hit the global optimum here. But I doubt that you will be able to find a single static setting from this starting point to get you into the optimum. Now, if we were to actually switch the learning rate on the fly after the third step, right, after this step here, then we should be able to not just bounce out again and hit maybe this local optimum here, but actually stay in the true optimum region. And for that, I have manually adapted the learning rate after the third step, right? And you see, I have drastically reduced the learning rate from a very high value to a fairly low value. And we can actually stay in the region of interest and really find the optimum value in this region. Now, this is an example of how we can manually do this dynamic optimization to get to better results. And we often actually have done these kind of manual choices already in learning literature. So for example, we have many heuristics that tell us how to adapt our hyperparameters on the fly. We know for years now that learning rates should be adapted and decayed over time because we get closer and closer to optima, and we really want to exploit the hyperparameters so that we get to the true optimum or to a optimum rather than jumping out of the bowl again. We know that we should do restarts if no progress was achieved for a while, right? We see that in evolutionary computation, but we have also seen that work for deep learning again. And in Bayesian optimization, right, or anywhere where we have a budget attached, we do want to explore in the beginning, but the less budget we have remaining, the more we want to exploit the knowledge that we have already gained of the optimization problem. So we really want to hone in on the optimum at the end rather than exploring all the time. And these heuristics create many different schedulers, for example, in learning rates, for learning rates. And if you just look into the PyTorch documentation, you see there's a ton of different learning rate schedulers. And while they are great, they don't fully solve the problem because they come with their own hyperparameters. To give you an example here, let's look at the step decay, where given an initial learning rate value, you want to adapt it, for example, halve it after a certain number of steps. So if we look at the blue line, we halve it every 250 steps, and the orange line, we halve the learning rate every 400 steps. And you see, these behaviors are very different in terms of how the schedulers look like for the learning rates, and that also induces very different behavior in the actual learning of the parameters of your neural network. You can also have more complicated schedules. For example, cosine annealing with warm restarts is a very popular one, where again you come with it comes with its own hyperparameters, but in essence it behaves very similar, where you decay your learning rate over time, but it also uses some restarting mechanisms to jump back up again. So while we have this community knowledge that learning rates should be decayed over time, we do not have the exact formula that we can apply everywhere, and we need to adjust these schedules with their own hyperparameters to fit our particular problem at hand. And to take the take-home message for you here is that learning is often an iterative process, right? We traverse a diverse solution landscape, and that traversal requires adaptation to the hyperparameters. And dynamic optimization is actually able to handle these non-stationarities. So changing hyperparameters on the fly is really crucial. And we have so far discussed how heuristics, for example, could help us there. And it's also very important for you to recall that heuristics are a form of community knowledge and can help you already share some information across different optimization problems. But you cannot tell your colleagues exactly how to decay your learning rate, for example. You just can tell them, look, it's important that you decay your learning rate, but for your particular problem at hand, you will have to figure out how to set these hyperparameters, or what we can also do, which we will see in the remainder of the module, actually learn how to adapt these things over on the fly. With that, I'm very much looking forward to talking about dynamic optimization for the remainder of this module.